Let's do some Boolean algebra examples. Let's start with this expression A and B, A bar and C, B and C. Okay. What I like to do is to kind of take this expression and try to play with it and try to reduce some of the expressions. Let's look at it this way. If I were to implement this circuit using AND gates and OR gates, this is how I would do it. I would do A, B, C, A and B, okay, A bar and C, B and C. Okay, and then OR gate right here. So this is the F, the original F. Okay, how would I implement this? Well, if you look at an AND gate, I have an AND gate with I have an AND gate with 4 transistors, and to build a AND gate, I have to take 4 transistors here for the NAND. Okay, A, B. Okay, and then put an inverter. Again, 2 more transistors. So this AND function would require 6 transistors. Okay, and the same thing for this OR output. This requires 6 transistors and 2 transistors for the inverter. That's 8. So counting all the transistors here, I need 8 here, 6, 6, 6. Okay, and that's 18, 24, and then another 2 for this inverter here, and therefore I need altogether 24 transistors for this. Okay, let's try to reduce the number of transistors for implementing this. I'm going to take the first term and AND it with A or A bar. What is A or A bar? Well, A or A bar, we have seen that's 1 already. Okay, so if this is a 1, I can AND any term or any expression with a 1, and therefore ANDing B and C with a 1 is okay. So I'm just going to do that. Now, why I'm adding these, we will know later on. And therefore, I'm going to expand this to this form here. And then I'm going to use distributive law and then say A and B and C, A bar and B and C. So this term turns into this thing over here. And now I'm going to take the first term and the third term, use distributive law or factor A and B. The first one becomes factor A and B ANDed with 1 over C, and then the second and the third one, let's factor A bar C, and then that becomes A bar C 1 over with B. And therefore, this is the new way of writing this. I'm going to do A or B. A or B is a 1, and A bar and C ANDed with a 1 is A bar C. And therefore this becomes this, and this becomes this. And therefore my new expression is A and B ORed with A bar and C. Actually, I'm showing that this term here wasn't even necessary. Let's do a De Morgan's on it, double bar it, A and B, A bar and C. Break the lower bar, that becomes A NANDed with B, and then change the ORing to ANDing, A bar ANDed with C bar, and therefore this is an AND. This is an AND, this is an AND, and this is an AND, and the new circuit becomes A, B, C, an AND for AB, an AND for A bar C, and an AND for the result. Okay, let's count the number of transistors. This one has 4 transistors, 4 transistors, 4 transistors here, and this little thing here is an inverter, and inverter is uses 2 gates or 2 transistors, and then therefore I have a total of 14 transistors altogether. So by minimizing this, I was able to reduce 24 to 14, 10 transistors saved here. So why do we use Boolean algebra? For exactly what I'm showing, for reducing the delays in the circuit, or to manipulating the expressions to come up with smaller circuits, to save on transistors, to save on delays, to save on the number of gates, and so on. Alright, the problem with what I did over here is that the Boolean algebra is good, but the problem with Boolean algebra is you have to know the answer before you can do manipulations. I mean, when I look at this, how do I know B and C is the one that has to be expanded? Why didn't I expand A and B? Well, I would probably play with it a lot, and then finally found out that I would finally find out that that wasn't the right term to expand, and then I would go on B and C and then play with it long time before I finally realized that, okay, this is how we can reduce this. The reason for this problem is that Boolean algebra doesn't give us a good insight into what terms are, or how terms are related to each other. In order to get a better view of the terms in Boolean algebra, I like to be able to use a graphical representation. I like to have a graphical representation that would show me the relation between BC, AB, A bar, C, so that when I decide that BC is the term that I want to expand, I will be able to graphically see that. Okay? So Boolean algebra is good, but then the problem with it is not having a good insight into the circuit itself. For this very reason, we use Karnaugh Maps. Karnaugh Maps, we have Karnaugh Maps for, this is a 3-variable function. We have Karnaugh Maps for 3-variable function, 4-variable functions, 2-variable functions, and so on. Okay, we're not going to get into a lot of details of Karnaugh Maps, but we will talk about the basics of Karnaugh